So today I want to talk about integration of inquiry-based learning with real-world problem solving and what I've done at Wright State University to encourage inquiry-based learning, working and collaborating with various universities from Ohio to even Florida here. So how do we enhance inquiry-based learning and how do we help our students learn better science, technology, engineering, and math? Typically, when you're teaching, one of the things I always found, when you tell me something I forget, you show me, I remember. It's a typical Chinese proverb, if you involve me, I understand. So if you just memorize a formula and you ask a student kind of, how did you know, or what was that formula really telling you? They'll say, well, I just know I memorized it, but I really can't explain it in detail. Or if you have them drive a little further into the steps, they can't always explain it. So as a chemistry professor at Wright State University, I've been there 22 years, I'm a full professor of chemistry. I have found that when I'm doing even pre-service and in-service teacher workshops, that 2% of the new teachers in our school districts are actually going into the textbooks and just teaching from the text, trying to hit the content knowledge for them to hit the state test and pass that. So how do we step beyond that? How do we make sure that they have the activities and not just do step-by-step or cookbook labs, that they think and problem solve and do some critical thinking and creativity is built into the curriculum? So the goals of this inquiry-based real-world experience I'm going to talk about today was a project through the Ohio State University, is one of them I'm going to talk about, and how to develop inquiry-based labs that develop new knowledge. So in like the freshman chemistry course, we have to develop kinetics. We have to have content and kinetics. They have to understand a lot about oxidation reduction reactions. So how do we do that? How do we get them involved in an introductory laboratory with research skills, starting them out as freshmen, so we can build them to be researchers, even if they're pre-med? Because as you know, a lot of your medical doctors today, you'll go in, you have a problem, you explain it, and they don't right away get the answer. They're not, sometimes it's more difficult for them to analyze the whole situation. So how do we create problem solvers to do that? And I think starting at the freshman level is the way to do that. So I'll talk about some modules that we developed working with Ohio State to do that. Increase retention in the STEM fields is why we're doing this. That's why we're working together with our colleagues so that we will have more engineering and math majors and chemistry majors, because if you look in the United States, we're really hurting for engineering, math, and science. So how do we increase that and to keep our process going so we have jobs, people to fulfill these jobs as people are retiring? And collaboration with industry is vital. So one of the projects I talked to this morning about was OAIMA and Ohio Aggregate Industrial Mineral Association. So one of the things I did was work with the Ohio Aggregate and Bowser Warner Chemical Company to teach what they need in their actual job facilities. What are the type of people they're looking for? So collaborating with industry is a vital part so that your students will be ready for the real world, the next level, to make the next step. So the objectives of our research experience in our inquiry-based module is obviously to develop, implement, and evaluate these research modules to see how they're working. We've done that to see if they're successful or not. Looking at curriculum at all partner institutions, how to integrate in various institutions. I'll talk about all the institutions that work together. It was beyond just Ohio State University, but I created the electrochemistry modules for Ohio State. To increase the number of publications. As you know, undergraduates, it's vital for them to publish. And so I had an undergraduate student even that was from Greece, then came to the States, great student, went to a private school her senior year. She was doing a science fair, got involved with helping her with her science project, started her working in my research lab. She actually joined our university at Wright State, and it was quite a good thing because as she was doing research with me, she's got now 5 publications and she's only a sophomore. So how do we build students to have publications and learn about how to be successful scientists? So that's a goal for me as a professor to do that. And develop research modules that can work statewide, or I should say around the world, because these modules can be integrated in any curriculum around the world. Like the other day we talked about the dye-sensitized solar cell that could be integrated anywhere. So one of the things you want to do whenever you're doing a curriculum or putting something together is work across like communities in chemistry. So that's what I've done, and we'll talk about these partner schools. quantitative and qualitative data to kind of see what's going on, and the effectiveness of these modules, if they're working or they're not working, or how can you improve them. Because a lot of times you might create a module and it's not doing what you want, or the students aren't getting the content knowledge that you're expecting them to walk away with. So how do you do that? Well, you can improve by assessing them. They'll get more information. So in this, it's kind of hard to see because the color on it, but we had Miami University, Dr. Rich Taylor, he was an organic chemist, Ohio State University, which was the biggest thing in working together, OU, which is Ohio University, which is in Athens, and then we went on to, say, University of Toledo in Ohio. But we worked also, what was so fascinating, we worked with some community colleges, and so Sinclair Community College was one of those colleges, because those two-year colleges are very vital, because you're going to have students transfer from the 2-year to the 4-year. So it's good to build that communication. Analytical and environmental, obviously, my name's on there, so that was Wright State University. So there were 15 institutions, variety, but I was just showing you how around the state of Ohio, all these people came together. Built from that module that we have developed here with this particular program, I have expanded into the University of Central Florida, working on sensor development with Dr. Lee Zai and Dr. Alphonse Schulte, which I'll talk about later. So the characteristics of a research module is obviously is to have them explore the 5 E's of inquiry-based learning. The first one is engage, and then have them getting into exploring, of course. So integration of the core structure is very important. All phases of the research process emphasize the scientific method. Make sure you do that. Engage your students in the problems of societal interest. So for instance, if you're talking about the aggregate industry, today I talked about the OAIMA, the Ohio Aggregate Industrial Mineral Association, and how I created a module to talk about the topography of the land and to decide if you're going to mine your area of your land. Is it worth you to pay $1 million to drill 5, or actually $1 million for each hole, 5 drills, that's $5 million. Are you going to get your profit back? Are you going to be a good aggregate industry developer? So how do students learn to problem solve and do that? And that's the purpose of these research modules, is to make them think about that and working with society. So industry is a vital part of that. Working in groups and individuals sometimes. Today we had a question from one of our colleagues in the seminar, what was it good to do group? Well, group can be good. Sometimes you have to do group work, but then obviously individual understanding is important too as well within your project. And transferability is saying how can they adopt it? Is it sustainable? Is it going to be disseminated, this knowledge that they're taking back? So Martin Chalet, I won't read exactly what he said, but just you can read it there yourself. But the main goal he was saying when we were young kids, what did we do? We like to investigate, play with things, analyze them, kind of look and see what's going on. And so in inquiry, in the 5 E's, you're doing like a kid. You're becoming creative. You're thinking about it. You're problem solving. You go back. You might reiterate, go back over something, and then try to make it better, even if you're playing with Legos. So how does students problem solve? It's very important. We do it as children, but we forget teaching it really helps students learn. So in an inquiry, I think most of you know this, you're going to ask a question that's going to be problem-based for them. They're going to plan and conduct an investigation. They're going to gather data, think logically, and communicate their scientific arguments. That's a vital part. So we're talking about traditional versus inquiry. And so traditional, you're just giving a lecture, where in the inquiry, the student is going to be solving the problem. You're just facilitating the lab. You're not going to supply them the answer. You're going to make them think about, do they want to use poly-3-methylthiophene as a polymer? I'll talk about later. Or do you want to use poly-2,2-bithiophene? Or could you use both of them as a sensor for neurotransmitters in the brain to teach oxidation reduction reactions? The class structure typically, and anytime inquiry-based learning works best when it's a small classroom. That's not to say in a big lecture hall that you can't create some type of IBL learning, because you can, but small classes are much easier to deal with. Doing this, integrating the emphasis in addressing student misconceptions is very vital within a module to make sure you think about that. So cooperative learning environment's perfect, and some of these other things I've talked about, assessment is vital. You'll see assessments on the list. So here's our assessments, pre and post test. So how do you see if your module was successful or not? You're going to do a pre-test, and then you do a post-test, as R.R. Hakey talks about in the literature. And if you see a content gain of 0.5 and greater, typically that's a good sign that you do have a good successful module. Horizon Research questionnaires, you can purchase those. Those are very useful to know if your students are, what are they, like, how are they thinking? What is the development of their process? And then reflection obviously is very vital too. So this is the RR-Hakey model, and just in case anybody wanted to use it to calculate the gains in your classroom, this is a really good way to assist and see if you have a content gain in your student learning. You take a post-test minus the pre-test, and then divide by 100 minus the pre-test is how you calculate that with the normalized gain. And so what I was saying is if a normalized gain is like between, I say theoretically between 0.4 and 0.7, you know, it's like medium gain. If it's 0.7 and greater, you have a really high gain. And typically lecture modules have been showing that they're 0.3 and below. And so you can see your students are not retaining the knowledge when you give them a test. So it's really important. I think this was a very good module here that this young lady was doing with the art. She was engaging them, making them present, making them problem solve, and interacting with the community. And that's they keep that the rest of their life when they walk away. So the electroanalytical chemistry engineering modules, just to talk a little bit about what they incorporated and how at Ohio State University and throughout the state of Ohio, how did we disseminate these modules and help? Well, one of the things in an inquiry-based module is we tried to also not only just look at electrochemistry techniques, when I say electroanalytical chemistry with engineering modules for the freshman level, but we also looked at other types of equipment, instrumentation students should know about. Like when they get to organic chemistry, they have to understand Fourier transform infrared spectroscopy, looking at bonding. Do you have this morning we talked about hydrocarbons, do you have an OH group, or do you have a aldehyde group, those types of things. So you can actually figure out the functional groups. The UV vis is another way you can look at if you create nanoparticles. That can be a lab. How do you know you really created the nanoparticle? Again, graphing is vital, putting the sample into the instrument and seeing, do you see a graph there on the Y and X axis showing you something that's supposed to be there for, say, a silver nanoparticle or a gold nanoparticle. Scanning electron microscopy, you can see where the engineering is kind of coming together with the chemistry, because that's a very important instrument to understand the morphology of a surface when you create your sensor. What does the morphology of the surface look like? It gives you an overall picture of that. And of course, the pre and post test outcomes. So one of the things I'm talking about here is carbon nanotubes. Carbon nanotubes are really great. They're graphene sheets. I'm sure you've heard about them. And they're used to basically give you an enhanced conductivity, say, for sensors. And they're utilized in a lot of processes for sensors. So they are honeycomb structures. And in terms of electrochemistry, we are teaching our students about how to integrate carbon nanotubes onto the sensors to detect, say, heavy metals to neurotransmitters in the brain. So a typical example of a carbon nanotube modified electrode, this workshop was done with Dr. Lee Zai I worked with Ohio State University on creating the electrochemistry modules, trying to learn about problem-based with Wright State University and how to incorporate taking monomers into polymers and growing them to, say, detect neurotransmitters in the brain. I started working with Dr. Lee Zai from the University of Central Florida, and it's been really valuable because now we're taking carbon nanotubes and we're taking polymers connected to those carbon nanotubes to give enhanced signals for, say, heavy metals to neurotransmitters. So these are examples of some of the chemical structures that were utilized, such as the polyvinyl alcohol with the carbon nanotube, the poly-3-hexylthiophene, the polystyrene sulfonate with the silver nanoparticles. Looking at the neurotransmitters to detect would be a catechol. So how can you look at different catecholamines? So a catecholamine in the brain has a 1,2-dihydroxy benzene ring, but you could rotate and have, say, another structure here. That could be dopamine once you added an amine group in the brain. So there are various neurotransmitters in the brain. So once you create these sensors, do they detect the neurotransmitters in the brain? And the presence of ascorbic acid. Does anybody know what ascorbic acid is? Vitamin C, perfect. So vitamin C is a vital part of your diet. And so when you're trying to detect neurotransmitters in the brain for the sensors these students are developing, they have to also have the interferent, which is vitamin C, to see if their sensor still works. And another interferent is uric acid. So you can see it's a real world application, I think, is what kind of excites the students. So a 3-electrode compartment cell is very simple to set up and teach them about it. The auxiliary, the working electrode is what you're coding, that's your sensor, and the reference electrode. And so this is just another example of reiterating about a different type of polymer you can use, such as poly-3-hexylthiophene, versus you could take that and change it to poly-3-methylthiophene or poly-2,2-bithiophene to make it more problem-based for your students. This allows students, I talk about this even in early and middle school education, K through 12. Our students really struggle with reading a graph. I have found this on tests. So I think it's really important to see on the y-axis we have current, on the x-axis we have potential, for them to understand that as they look at this picture, they have an oxidation peak, another oxidation peak, and a reduction peak. And that could be what we're disseminating in the same concept in the brain, that you can have catechol, which is the oxidation reduction, and this would be the ascorbic acid. So you can see that this sensor works. But if a sensor didn't work with the carbon nanotube with the poly-3-hexylthiophene, this peak could be missing and this peak could be missing. Typically, when your sensor doesn't work in the medical field, so you see we're trying to train people to even be doctors. If they want to, we're engineers to create sensors for the medicinal field of study, that right here, this could be completely gone is what typically happens. So this was a successful sensor created by a student. This is a really good example, too, of differential pulse photometry. So we look at cyclic photometry and we look at differential pulse photometry. Why differential pulse photometry? Because you're looking at lower levels, lower detection limits. So as you're looking at lower detection limits, you have to try another technique to teach your engineering students, your chemistry majors. And you can see we have a little bit of noise in the system, but the student was successful at getting, with this carbon nanotube polyvinyl alcohol, they can get low amounts, low concentrations of AA and catechol together instead of just getting one peak, which would be an unsuccessful sensor, but here we have a successful sensor. This just shows the scanning electron microscopy that the students really get to see about what a picture looks like, because when you talk about it, it's an image, it's a picture, but they really don't believe you until they run the instrument and put the sample in, and we have someone to help them run the instrument, but they get to see the constituents of the carbon, the sulfur, what is in this structure of the electrode that we created is carbon and sulfur. So they see that it's really true. They put it on the surface. This is an example of an environmental lab that you could create with lead and cadmium. Lead and cadmium detection in the water is vital. Today we had a person talking about how to detect, say, in the oil fields where they come off and they leave a waste spill and there's high amounts of salt and nothing will grow once they've left. And the cattle ranchers are really upset because now their water is contaminated and nothing will grow in the field. Same concept. Well, a lot of times what happens also in certain areas, you can have heavy metal contamination, and this could be lead and cadmium. So the student gets to learn about taking a carbon nanotube with this is a polymer, polystyrene sulfonate, with a silver nanoparticle, and detecting this peak as lead and this peak as cadmium. And the student gets to learn that sometimes, you know, with the sensor, things aren't perfect. I mean, at least we get two peaks. We get lead and cadmium. There's a little bit of noise in the system, so it's not perfect, but we're getting a detection. Just another example of an SEM and how to work with colleagues among our area, such as UCF with Wright State University, which is in Dayton, Ohio. And you can see here the different techniques we're talking about: cyclic photometry, differential pulse photometry, square wave anodic stripping photometry. Now, why square wave anodic stripping photometry? Because when you're looking at heavy metals, the student learns about reading the literature and saying, oh, CV is not going to work, cyclic photometry, for really low concentrations in the water. We're talking about parts per billion. So you need to go to square wave anodic stripping photometry, which is another technique. So why is this important? We are actually collaborating with AK Steel and Bowser Morner for some of our projects as well in Ohio to see what they need our students to learn as well, and share with them our modules to make sure they're hitting the real world things that our students should be doing when they get into industry. I think that's important. So I won't show every single graph because most of you are not chemists, but I can show you, for instance, varying parameters is a really important thing for students to learn in problem solving. So when they grow a monomer onto an electrode surface that becomes a polymer, you don't tell them the exact parameters as freshmen. I mean, it might be a little challenging, but you can guide them, but they should learn that they have to look at, say, the potential of growing it is a factor, temperature is a factor. So they need to look at these other factors as they're developing a module. And the delta E, the closer the delta E, the more reversible the sensor is to detect neurotransmitters in this example. So this just shows you other topics, examples of another polymer, poly-2,2-bithiophene, to detect catechol and ascorbic acid. Now look here, this is very interesting. So this graph is turned the other way, but look, we switched the scale. We're going from 0 to 800 this way. We'll say millivolts. It's in volts right here, which 800 would be millivolts, as you guys know. But since we switched the scale, the oxidation is on this side and the reduction's on this side. So you see how we want the students to think about graphs and problem solving? Look at the x-axis and the direction it's going as well. Mercury ions was another metal that was very interesting. And mercury ions encapsulated with, say, a polymer might be a way to remove heavy metals out of water. So this was a project I gave a student to see if the student could solve the problem, and learning about taking a polymer and encapsulating it, and the student found that poly-2,2-bithiophene was a polymer because it had a sulfur in that polymer. It could actually encapsulate into the mercury and remove the contaminant. So that's a possibility. So learning how to utilize sensors, I won't go through every single slide, but learning how to remove heavy metals, sensors that can, or any type of polymer that can remove heavy metals helps you see that. And here's the morphology of the surface. Very important to see if there's a difference in the morphology. And then learning more technology. Instead, now here we're looking at X-ray fluorescence. So what you're getting out of that is these investigations will continue in order to determine the mechanism and interaction, say, a heavy metal. So students are going to keep working on problems and keep looking at things in real-world parameters such as temperature and pH. Like today we said in the area where the oil was a spill and nothing would grow, the salinity levels were too high, but also the pH levels were quite off. So that gives you a lot of information. And then these students that they had at another university were doing the same concept. They had to problem solve and figure out how to clean up the soil. And that's what we try to do. We try to engage our students and make them problem solve and collaborate with people around the area that are interested. And so Dr. Lee Zai was one of our colleagues interested in that. Dr. Alphonse Schulte, I didn't get to share to you. We also taught him about Raman spectroscopy. He's been very helpful with that, even though I didn't show some of that data today. And Ohio State was very helpful because they had a National Science Foundation grant, which allowed us to work together to create modules to give us money to travel and do these projects, field trips with our students if we needed to get heavy metals in water and look if they work or not. Faraday Chemical Company is a very essential part around the Dayton, Ohio area to work with as well, because they are a company that actually does electrochemistry. A lot of students don't realize electrochemistry is a really important study. In the freshman chemistry, we cover oxidation reduction reactions, but they never get to see an electrochemical instrument. So thanks to the grant from Ohio State University, they actually get to get on an electrochemical instrument and actually learn about oxidation reduction reactions better. Bowser-Morner, very important because of in AK Steel, we're looking at the aggregate industry. AK Steel is building steel, but also within that, they're interested in solar cells to save energy. So you can see how all this cycle comes together, working with industry, seeing what our students should be doing so our students can get jobs. You know, as professors, it's publish or perish, but for students, it's go to college, but the goal is to get them jobs. So how do we make it where they're meeting the needs and the goals of the industry so we can get problem-based people that are experienced and ready to go into the field and make some money and not be out of a job, or they can't get the job, or they have to change their study because they can't meet those needs. So my goal as a professor at Wright State is to meet those needs. So I think that's all I had to say to you about my project.